Welcome to another video from Lockdown Electronics with me, Bill, and this time we're going to take a look at a couple of test meters. And I say test meters because one is a multimeter but the other one is a clamp meter. It's the Kaiweets HT206D in this case, and the other meter is the Kaiweets 601 smart multimeter, which you've seen before. I'll put links to those videos later on. The clamp meter is interesting because it allows you to make what I'm going to call non-invasive current measurements, which is potentially quite useful. And I don't always think people who are into hobby electronics would necessarily think of a clamp meter as being a useful addition. So we'll have a look what it can do, and as I say, both meters were provided to me to review by Kaiweets, so thanks to them for that. Probably worth taking a look at their website, which actually is very readable and has got lots of information. It's particularly worth having a look at the Kaiweets story, as they like to call it, because these guys are a bunch of engineers who go around scouring the place for instruments that they think are reasonable quality, and so they provide a range of instruments, not just electrical testing but other things as well. I'll put a link to the website, and I'll also put a link to the Kaiweets story in the description below, so I'd encourage you to take a look at that. It's not too time consuming to read it. So let's start by having a look what we've got. Here are the two meters in question, and I just want to start by saying that both meters come with a carrying case. In the case of the KM601 it's quite substantial, but the HT206D has also got a very good case. And although this is irrelevant in the lab, it's very handy if this is the kind of meter you're going to keep in a toolbox with other tools, because it actually stops the instruments from getting damaged and hopefully preserves them for a little bit longer. So by the miracle of filmmaking, let's have a look at the meters. And here they both are. The KM601 smart meter, you've seen that in previous videos. I've done a review. I'll put a link up top to that for you. And here is the HT206D. It's also got a big brother, the HT208D. Kaiweets actually do a range of clamp meters, but the 206 and the 208 both have a feature which the other ones don't, which I want to have a look at a little bit later on. And the reason I wanted to compare a multimeter to a clamp meter today is because I think if you're a hobby electronics kind of person, you probably just naturally go for a multimeter and wouldn't necessarily consider a clamp meter. And maybe that's absolutely fine, but the clamp meter does have some quite useful features which are potentially very handy if you're doing certain aspects of electric and electronic things. And it's also capable of doing quite a lot of the other things that a multimeter will do. So I want to compare and contrast today. Both have their place, but certainly I wouldn't just dismiss the clamp meter as being something that you see electricians using, because it is capable of a great deal more. Right, let's start by just having a look how meters measure current. Okay, before we get going properly with measurements, I want to start off by just quickly looking at this instrument here, for probably three reasons really. First one is it's entirely nostalgic. This is the meter that I bought as a young teenager, so we're talking at least 50 years ago, when good old Maplin was still on the go in Britain. In fact, 50 years ago Maplin were still a relatively small organisation, and this meter was your classic hobbyist's analogue meter. And the kind of accuracy you'd get from there, most hobbyists were quite happy with. These days we're disappointed if we can't get a couple of decimal places off a hobbyist's digital meter. So it's a nice way to think about how things have moved on. But the reason I've got this meter out is it's very easy to show you on here how multimeters, i.e. these two, actually measure current, because clearly the meter itself has got quite a delicate operating mechanism, and certainly isn't capable of handling 10 amps, which is the highest range of this one, and indeed this one too. So I've taken the back off this, so we just have a quick look, and in the back we've got a very old-fashioned circuit board. I'll turn it that way so it's easy get a better view. And we've got the meter movement and a buzzer and the fuse and a few other bits and pieces that you're going to recognise, and a couple of AA batteries went there. And what's probably most noticeable is that bar running across there, and if you can see it here, a large wattage resistor, and that large wattage resistor and this bar form the 5 to 500 milliamps range. That'll be that resistor there, and the 10 amps range is this metal bar here. And if you look, that metal bar is connected directly from common to the 10 amp socket. So when you're measuring current using the 10 amps range, it comes in there, goes through there and goes out there. And if you measure the resistance of this bar, you'll discover it's a great deal less than 1 ohm. And what we've got here is a shunt, which it's a term you may have come across. And what these multimeters do is they simply measure the voltage across the shunt, and then we just make use of Ohm's law. So we've got V equals IR. So in this case we know R and we know V, so it's simply a case of arranging the electronics so that they display the current. And that's how multimeters measure current, and it's also quite obviously the reason why there is a limitation on just how much current a multimeter can measure directly. Okay, now I will get these set up and we'll have a look at some current measurements. Okay, so to use a multimeter to measure current, then we need to actually put the multimeter in series with the load. So I've got here a variable AC power supply. I can get about half an amp out of it, so I'm going to be a bit careful. And I've also got here a automotive bulb. It's actually a 21 watts at 12 volts, so I'm not going to be running it up to its full brightness, or that's going to overload my AC power supply a little bit, and I don't want to do that. So what we've got, we've switched the meter on, and what's quite nice about this meter is that we'll put the negative line into common, and what's quite handy is at the moment the meter's searching, but if I now plug into the 10 amp range there, it knows straight away we're going to use amps. Now I want AC, not DC, so I'm going to change to AC. It says true RMS there, and so that's the meter in series. It's reading about 0.8 amps at the moment. I don't know how well you can see that on the camera, but the bulb is sort of dimly glowing there. So what I'm going to do is I'm going to increase the AC voltage incoming. I'm going to go up to about 1.2 amps. If I go much more than that, I'm going to overload my power supply, but you can see the bulb brightness increasing, and you can see the meter is measuring the AC current. Just ease it somewhere at about 1.2 if I can. It's a little bit fiddly on the voltage adjustment. Hopefully we get there in a moment. There we go, that's about as close as I'm going to get. So it's 1.2 amps now, and 50 hertz. So yeah, that's absolutely fine as a way of measuring current, but obviously you do need to be in series with the circuit. That's probably easy on a breadboard. It's less easy when you're for instance trying to measure the collector current of a transistor on a circuit board. That becomes a faff then. So let's now have a look what we can do with the clamp meter. So we've got two current ranges. This is the HT206. We've got 600 amps and we've got 60 amps. Whoops, there we go, 60 amps. And again, it defaults to DC, but I'm going to just change that to AC. And so that's now reading 0 amps AC. And so the first thing to note with the clamp meter is that if you simply do that, and I appreciate you're going to struggle to see that, let me just reposition that a little bit. As you can see, it's reading 0, yet we know there's at least 1.2 amps flowing through there, so that's something not quite right. And if you think about it, the clamp meter is actually working like a transformer, and this is one turn on the primary, if you like, and the secondary is a number of turns in here. So putting that in there, I'm actually putting both current directions in. I'm putting the in and the out in, and obviously that's oscillating 50 times a second, as this meter is telling us. So that's not going to read anything at all, because the measurements cancel each other out. So just show you that again. So that's 0 there, hopefully you can see that. But now I'm going to put it through just one of these connectors, and it doesn't matter which one. And straight away, as you can see, it's measuring 1.22 there, something like that. So we're getting a completely non-invasive method of measuring AC current. Now just bear in mind, I'm right at the lower limit of this. I don't have facilities to test up to 60, or certainly not 600 amps, but it's more than happy here measuring 1.2 amps, which is what we're getting on both meters. So the handy thing about the clamp meter is, if you need a quick and dirty method of measuring current draw, you can just pop it somewhere onto the circuit there, and there we are, hovering between 1.19 and 1.21, which is what we're getting there. So as I mentioned before, yeah, this is working a bit like a transformer picking up the AC, and we can prove that if we've got about 1.2 there. But if I now carefully wind a second turn on, if I can manage that, so we're at about 1.1 there, and as you can, well, should be able to see, whoops, I've pressed the hold there. Right, so now we've got 1.2, we've got 2.4 here, because we've now got 2 turns on the transformer, which sort of proves that yes, we've got a transformer arrangement going on here, and that's how the clamp meter is sensing the AC current. So it's done by electromagnetic means, really. And I suppose if you've only got a clamp meter and you want to make some sensitive current measurements, you could wind several turns on and then simply divide the result by the number of turns, and that would potentially give you the ability to read a lower current. So that's AC operation, and that's certainly what you quite often see clamp meters doing. So here's just a screen grab of the Kaiweets clamp meter range. As you can see, there's a set of them, and the highlighted one there, the HT206D, which is the one we're looking at here, is capable of DC current, as is the 208D to the right. That's also capable of inrush current measurements. Again, I've not used the 208, so I can't speak, but that has the ability to spot the starting current of a motor, for instance, which can quite often be considerably higher, and I think it does that for the first 100 milliseconds, something like that. So that's potentially handy for working with big inductive loads starting up, such as electric motors. So as I say, 206 and 208 both do DC current, so I'll reset the bench up now and let's have a look at DC current. Pretty much the same arrangement in terms of the circuit. So I've got DC supply coming in here now from my bench power supply, and I've got the same automotive bulb here, you see dimly lit, and I've got it currently set to about 1.2 amps. I've just changed the meter setting from AC to DC, so we're reading that. So again, the meter is in series with the circuit that we're measuring the current of. Now, as I mentioned, 206D and 208D both do DC, and I think the AC operation is probably relatively easy to visualize, because effectively this is half of a transformer here, and by putting a wire through there, we're effectively putting a single turn through as a primary, and that's allowing the meter to sense it. With DC, once the power is on, there is no change in the magnetic field around the wire, so there'd be nothing for the meter to sense if it was using in the transformer mode. So most clamp meters, and I've not torn this down, so I don't know, but most clamp meters that work with DC have an additional Hall effect sensor, and I've done a video on Hall effect sensors. I'll put a link up there to it so you can see them in operation. But essentially a Hall effect sensor is a semiconductor which is able to be sensitive to magnetism. And so what we need to do when we're taking DC measurements, you can see just with the meter in my hand there, it is ticking over and showing a reading. So what we need to do is we need to hold the button here until we get a beep, and we should be able to then zero the DC calibration. It's important you do that before you take a measurement. So now let's take a single wire, let's pop it through, and hopefully you can see saying about 1.29, yeah, something like that. If I can just get the wire to stay in the right place. Let's try it like that. There you go. So it's about saying about 1.26, so we're certainly pretty close, considering that's a completely non-invasive DC measurement. Now I hear some of you out there say, well, it's not accurate. Just have to remember here that the really handy thing about being able to measure DC current like this is the non-invasive bit. And obvious applications for me would be in the automotive world, where you've got cables that could be carrying 10 or 20 amps, and it's more than possible to make measurements like that. So for instance, and I haven't got a power supply really capable of driving this, but this is a main beam incandescent headlight bulb, 55 watts, so that should be drawing about 5 or 6 amps when it's on full power. And obviously, you know, you get that's just a car bulb, and usually have 2 of those in your headlight system, so straight away you're up to about 10 amps. So you're at the limit of a conventional multimeter, plus the fact you've got to somehow break into the circuit to take the measurement. So the ability to be able to just do that gives you a very handy way of checking DC current, with the proviso always that you need to remember to do the zero calibration, just to allow the Hall effect sensor to make the best job it can. 1.26 that's saying now, that's even closer. So just bear in mind again, I'm on the 60 amp range, so I'm right at the bottom end of the range. And can we put 2 turns on and get double the reading? Well, let's have a look. And actually the answer is yes, we can. So whilst using an inductor is obviously a bit of an issue with an AC circuit, you could potentially make several turns on here in a DC circuit without affecting the circuit performance, and then you could divide the result by a number of turns, which might give you a bit more accuracy or enable you to read down a little bit lower. I've tried this, and it does seem to be happy to read down into the certainly below half an amp. So I'll just back off the current 0.75 amps on the KM601. So there's your, that's about 3/4 of an amp, and yeah, 0.78, so it's measuring that very nicely actually. So there you go. That's the really handy thing about clamp meters that can do DC current. And again, you know, maybe that's all the current measurement you need in your lab. If you're going to need to measure microamps and milliamps, okay, then you need a multimeter. But if you're going to be using this for slightly higher currents, then it's very handy. I actually keep one of these in the tools in my camper van, because it's just a handy thing to measure how much current is being drawn out of one of the 2 batteries in me camper van. So okay, that's AC and DC current. We've reviewed the KM601 before. Let's now have a look at what else the 206D can do. Okay, so let's just have a real quick look at what else this meter can do. So I've now attached the probes that come with it. There's also a thermocouple for the centigrade and Fahrenheit readings. I won't bother going through that, but you attach the thermocouple in the normal way. Now, because this meter measures current using the clamp, there are only 2 probe connections, so you can't get that wrong. And then we've got volts, AC and DC, which I propose not to show you. It does work. It's a digital multimeter, that's what they do. So we've got, first of all, let's have a look at capacitance and resistance and diode check. So I can turn the backlight on, that makes it a little bit easier to see on camera, and if I do a long press on that, it turns this little torch light on here on the clamp, which don't know actually how much use that would really be, but everything seems to have a torch on these days, so I don't know, I tend to use a torch when I want a torch. That's very old-fashioned of me, isn't it? I'm trying to position that so you can see it easily. I'll try and keep turning the light on. So let's first of all do resistance then. So I've got a couple of resistors here. This one is 22 ohms. The meter's making that 20.9, can't argue there. And this one, which is supposed to be 8.3 mega ohms, actually on the LCR meter measures at 8.1 something. So the meter's making it 8.09, so it's pretty good at the two extremes of resistance. Now, one of the things multimeters do sometimes struggle with is capacitance. So let's now go to capacitance. That's now reading 0 nanofarads. So here's 10 nanofarads. 10.05, can't argue with that. This is marked as 300 nanofarads. Actually, it's about 320 on the LCR meter. That's saying 318. Moving on to some larger ones, 100 microfarad electrolytic. So it will take the meter a little bit longer to come up with the reading here. And I'll turn the backlight back on. That's saying 108 microfarads, which isn't far off. And finally the largest one I've got here, which is a 470. So you should see the display go blank as it takes the measurement, and that's saying about 479, something like that microfarads. So that's pretty good. Okay, let's whiz on to diodes. And again, so there we go into diode mode, and what I've done is I've got a couple of LEDs because they should indeed show up as diodes, but they should also have different forward bias voltages. So that's reverse bias, and indeed it is 0. Same for that one, that's reverse bias. So now let's see what the forward bias is on a green LED. That's given me 1.87. Apologies, that keeps going off. 1.87. And then this one should be higher, 2.58 on the white LED for the forward bias voltage. So that's pretty good, really. Can't argue with that. And let's now just have a quick look at frequency. So we'll go on to hertz there, and I've got the signal generator attached here. And currently I've got a frequency of 17 megahertz. So let's just, oops, it'd be better if it was connected, wouldn't it? Now you can hopefully see that there. It is indeed showing 17 megahertz, and that's where it topped out. I couldn't get it to measure any higher than 17 megahertz. But if I just step down there to say 13 megahertz, you can see it's responding quite well. And that's 10 megahertz, and we just one digit out there, and it was consistently one digit out right down to about 100 kilohertz. So for being able to measure up to 17 megahertz just on a ordinary pair of probes like that, I thought that was pretty good. So hopefully what you're seeing there is that's potentially good in the electronics lab, and it's also good if you want to measure high current, particularly the DC component. As I mentioned earlier, the use in the automotive world is probably the most significant one, and as I said, I do keep a clamp meter in my camper van for that very reason, so it's easy to make DC current measurements without having to disconnect anything. Okay, well that's 2 meters for you, a conventional multimeter and a clamp meter. And if you've not considered a clamp meter, maybe it is something you ought to consider, because it's not different to a multimeter, it's complementary, I would say, and I think there's a place for both of them in your toolkit or on your bench. And as I've highlighted some of the important features of a clamp meter, so hopefully that's made some sense. If you're thinking, I wouldn't mind one of them, please check out the links below. If you use the links and you use the code, not only will you get a discount, you also help this channel, and I would appreciate that, as that's pretty much the only way I do get support for the channel.
So thanks very much for watching. If you've not subscribed, please click the subscribe. It's especially good if you could click the like button. The more a video is liked, the more it gets offered to other people to view, and that would appreciate you doing that for me. That would help the channel. Thanks very much for watching. See you on the next video.